If x be two element set, then x to the power omega be uncountable. We have to prove that. Okay, how we prove this one? We simply prove it by construct a function g z plus 2x. Okay, x to the power omega. Then g is not surjective. Then g is not surjective. Okay, for this purpose let us denote Gn as follows. Gn equal to xn1, xn2 and xnm, where xij are 0 or 1, where xij are either 0 or 1. Okay, then we define an element y, define an element y equal to y1 y2 yn, they of x omega, by letting yk equal to 0 if x n equal to 1 and 1 if x n equal to 0. Then the particular element xn appear in diagonal entries in this array. Then the particular elements xn appear in diagonal element. Okay, now y, so that nth coordinate differs from the diagonal entry, and y so that the nth coordinate differ from the diagonal entry. Now y belongs to x omega and y does not lie in the image of G. Now given n the point Gn and the point y differ in at least one coordinate. Okay, given n the point Gn and the point y, the point Gn and the point y differ in at least one coordinate. Differ in at least one coordinate. Namely the nth coordinate. Thus G is not surjective. Thus G is not surjective. Okay, then how we construct this one? This g equal to z plus 2x omega, then g is not surjective. Gn equal to xn1 xn2 xnm, where x is ij are either 0 or 1. Then define an element y of x omega by letting yk equal to 0 if xnn equal to 1 and 1 if xnn equal to 0. Then the particular element xn appears in the diagonal element y, so that at the nth coordinate differ from the diagonal entry. Hence y belongs to x omega. Y does not lie in the image of G. Given n, the point Gn and the point y is differ in at least one coordinate. Okay, then one coordinate, and this coordinate be nth coordinate. Okay, this coordinate is nth coordinate. Then y is not surjective. So 0 1 to the power omega is an uncountable set. Understand? Now we proceed further and yes, the portion also. Now we're going to another theorem. Let A be a set then there is no injective map. If and there is no surjective map. Now prove. In general, if B is non-empty set, the existence of an injective map implies that the existence of a surjective map. And one defines GC equal to F inverse C for each C in the image set of F. For each C in the image set of F, and defines G arbitrarily on the rest of C. In general, B not equal to phi be a set. The existence of an injective map FB to C implies the existence of a surjective map GC to B. One defines GC equal to F inverse C for each C in the image set of F and defines G arbitrarily on the rest of C. Therefore, it suffices to prove that given a map GA to PA, the map G is not surjective. Therefore, it suffices to prove that a map GA to power set of A, the map G is not surjective. For each A belongs to A, the image GA of A is a subset of A. Which may or may not contain the point A itself. Let B be the subset of A consisting of all those points A such that G does not contain A. B be the subset of A consisting of those points A such that GA does not contain A. Now B is empty or it may be all of A. but that does not matter. We assert that B is a subset of A that does not lie in the image of G. So we assert that not so. B is a subset of A that does not lie in the image of G. For suppose that B equal to GA0. For some A0 belongs to A. Now by definition of B, we erase these things. Now by definition of B, A0 belongs to B implies and belongs to B implies and implies that A0 belongs to A minus GA. CA0 implies and implies that A belongs to A minus B. So in either case we have a contradiction. Okay. Then we done this proof. Then first we say that B is non-empty. Then the existence of injective map A B to C implies that the existence of surjective map G C to B. But define G arbitrarily on the rest of C. Therefore, it suffices to prove that GA2 or set of A, the map G is not surjective. For each A belongs to A, the image GA of A is a subset of A, which may or may not contain the point A itself. Let B be the subset of A consisting of those points such that GA does not contain A. Then now B be empty or it may be all of A. We assert that B is a subset of A that does not lie in the image of G. For suppose that B equal to GA0 for some A0 belongs to A, then by definition A0 belongs to B implies that A0 belongs to G minus GA0. This implies A belongs to B minus A minus B. This is contradiction. So we get this one, GA2 PA, the map G is not surjective. Okay. Then we going to, there is no injective map P, the power set of A to A. Now we prove another problem. A and B have same cardinality. Then two sets A and B have the same cardinality. if there is a bijection of A with B. If there is a bijection of A with B. Now we have to show that if B subset of A and if there is an injection if there is an injection F A to B, then A B have the same cardinality. Now define A1 equal to A, B1 equal to B, and for A greater than 1, AN equal to FAN minus 1 and PN equal to APN minus 1. Then A1 subset of B1, subset of A2, subset of B2, subset of A3, dot dot dot. Then define a bijection H A to B by the rule Hx equal to Fx if x belongs to An difference Bn for some n and x otherwise. Then HV bijection, so we tell about that A and B have the same cardinality. Okay. Then cardinality of A equal to cardinality of B. Okay. Now here we stop.